Hello. How do you guys like the intro video?
I love it.
Always the best videos.
Yeah, that's why that's what I spend my time on, creating these intro videos. Anyway, hello everyone who's watching. Say hi if you're here, of course. So this is the first 1 out of 3 sessions that we're doing this week, which we're calling Cilium Week. Maybe we should call it like Cilium Half Week because it's not really a full week, but you get the idea. We did the similar thing with Mesh, so we figured let's do something similar with Cilium, especially because they announced a Cilium Certified Associate exam, or CCA, which is coming soon. Let me share my screen. But anyway, I'm Peter. Marino Alessandro. I don't know if you guys want to introduce yourself briefly while I'm sharing the screen here.
Yeah, I'm Alessandro, based in Amsterdam, one of the developer advocates at Solo, and love Cilium, love Istio, love Kubernetes, love everything.
Yes, and I am Marino Widjay. I am yet another developer advocate at Solo up in Canada. And the best part is I am chill for the next couple of days while these two fantastic gentlemen take over and run the show. And I will cover off Friday where, I don't know, we'll get into some deep stuff around some deep networking. Yeah.
I always sign up for the first thing because I always feel like, let me do the first day and then I'm done, but no, it's gonna be great. Hi Uni. It's great that we have some people joining in as well. Everyone can see my screen, I'm assuming. I can make it a little bit, well, it doesn't really make it bigger, but let's see. Maybe like this. Yeah, this looks better, I think. So this is the page for the Cilium Certified Associate exam. I'll post it in the comment. I don't think you can apply for a beta test if you're interested. You can't. It's not available yet. It's coming soon. But this will be an entry-level cert targeted at platform or cloud engineers who are interested in networking security and observability. Now, if you watch the Mesh week, where we talked about the Istio exam, so that exam was hands-on with, I think they call it performance-based items, where you actually get an environment and you solve the problem on a cluster with Istio installed and whatnot. This exam will just be multiple choice exam, so there's not going to be a practical part associated with it, right? So it's just going to be multiple choice questions, and the domains and competencies are listed here. So let me zoom this in, and this is how we structured our, like, these today and then tomorrow and Friday. We basically, today we're going to talk about the architecture portion. We're going to talk about the eBPF a little bit, and we'll talk about installation and configuration today. So we move the things around a little bit. And then tomorrow we will do network policy and network observability. And then there's something else tomorrow, right? Let me take a look. Do you guys, Marino, do you remember what was on day 2? Oh no, day 2 is network policy and network observability. And then day 3, we're doing BGP and external networking, service mesh, and cluster mesh, right? So we will be covering all of the topics here, but we just kind of moved them around a little bit so it fits into 3 days, right? But we'll cover more or less everything. All right, so let's get started. I am sharing my screen, but let me actually share the slide deck properly. There we go. So this will be better. And of course, let us know if the font is too small, or if we need to go faster, slower. Or of course, if you have any questions, feel free to ask in the chat, and we'll try to answer them. There's 3 of us, and I think between the 3 of us, we should be able to answer those questions, I guess. But anyway, so let's get started. So agenda today, as I mentioned, we'll talk about architecture, role of Cilium, IPAM, IP address management, Cilium components, data path models, and eBPF. And then the second section will be today installation and configuration, where we'll do a demo of installing Cilium and then showing the Cilium CLI, and then running connectivity tests and monitoring status of the installation. All right, so let's start with the description. So what is Cilium? So from the cilium.io website, the description of Cilium is a cloud-native solution that provides for providing, securing, and observing network connectivity between workloads, and it's fueled by revolutionary kernel technology, eBPF. Typically, as with a lot of definitions, you have to dig in deeper to actually figure out what it means. So I'll start with the network connectivity between the workloads and then explain what that means. But in order to do that, we have to understand how networking works in Kubernetes. So I'll talk about this a little bit. So Kubernetes relies on container network interface, CNI plugins, to assign IP addresses to pods and then to manage the routes between all the pods. Kubernetes does not ship with a default CNI plugin. However, the managed Kubernetes offerings, if you go to AWS, Google, all the other clouds, they have a pre-configured CNI. So in Kubernetes, there are typically 4 networking problems that we have to solve. So we have to solve, how do we do container-to-container communication, pod-to-pod communication, pod to service, and then the external communication that's ingress and egress. So traffic coming into the cluster and then traffic exiting the cluster. So the container-to-container communication is solved by pods through the network namespaces. So the network namespaces in Linux allow us to have a separate network interface and a routing table from the rest of the system. So every pod has its own network namespace, IP address, and a port space. The containers within that pod can then communicate with each other through local hosts. So they share the same IP address and port. The nodes in the cluster have their IP addresses and a CIDR range for where they can then assign those IP addresses to the pod. So this will guarantee a unique IP address for every pod in the cluster. Now, the pod-to-pod communication then happens through these IP addresses. A virtual Ethernet device or devices are used to connect the 2 virtual Ethernet devices across different network namespaces. So in this specific case here on the slide, we have one virtual interface that it's connected to the network namespace in the pod, and then the other virtual interface is connected to the root network namespace that's set up on the node. Now, for each pod that runs on the node, there's this virtual Ethernet pair that gets created, and that's the one that connects the pod's namespace to the node's network namespace. So the traffic is going to go from E0 interface in the pod to the virtual Ethernet interface on the node side, and then through the virtual bridge to another virtual interface that's connected to E0 on the destination pod, right? So actually, sorry, virtual interface to the E0 that's connected to the target or destination pod. Now, one of the requirements of Kubernetes is that all the pods must be reachable by their IP addresses across the nodes. However, Kubernetes does not specify nor dictate how to achieve this. Now, if you assume that each node knows how to route the packets within the node, then the problem that we have to solve here is how do we get the traffic from each 0 on node 1 to each 0 on node 2. And this is where container network interface comes into play. Now, amongst other things, the CNI knows how to set up this cross-node communication for pods. So this the output here is from a kind cluster. So I use kind to run Kubernetes cluster, and kind uses a CNI called kindnet that runs as a daemon set. So there's one pod per every node. And that daemon set, that kindnet CNI, is then responsible for setting up the bridge between the nodes. And that allows one pod to call another pod using an IP address across the nodes. So looking at the routing table, we'll see that that's the first output that you have on the slide. It specifies, that output specifies where the packets should be sent. So there's an entry from the routing table on node 1. So the IP of that node is 172.18.02. And that specifies that, amongst other things, where the packet should be sent for pods that are running on node 2. So any packets that are destined to the IPs that fall into that specific CIDR range should be sent to 172.18.03 through edge 0, right? So that's how the CNI sets up the cross-cluster communication. So here's the diagram that depicts this. So we have two nodes, 1 and 2, and both of those nodes have different CIDR ranges. So the one on the left, node 1, is 10.244.10, and the one on the right, node 2, is 10.244.20. So if we're trying to reach the pod 10.244.22 that runs on node 2, what happens is that the packets will go from each 0 to the other portion of the pair through the bridge, and then from each 0 on that node, based on the CNI, the routes and the rules that the CNI plugin specified or configured, will reach node 2, because we know that the destination IP address runs on the node with that CIDR range. So it's going to go there, and then from there, each node knows how to route the traffic within the node. So that's a solved problem at that point already. Pod to service communication. So we know that pod IPs are unique. However, they'll also change whenever you recreate or scale up, scale down your pods. You'll always get a different IP address. So what that means is that you can't really rely on the pod IP, and you need a durable IP address. So the way that Kubernetes solves this is using a concept called Kubernetes service. So when you create a Kubernetes service, you basically get a virtual IP address that's backed by one or more pods. So when the traffic is sent to that service IP, it's going to get routed to one of the backing pod IPs. Now, in order for this to work, we need to answer a couple of questions. So first, how do we assign an IP address to the service? So we said it needs a durable, longer-lasting service. Secondly, how do we route the traffic that's sent to the service IP, and then from the service IP to the backing pod IPs? And then third, how do we keep the track of all these pods that are backing the service, right? Because pods can come and go, right? The IP addresses will change. So we need a way to track those IPs. So how to assign an IP address? That's an easy one to answer. So we can use the same approach as with pods. So we come up with a CIDR range and then assign an IP address from that range to the service. Typically, the ranges for services are different from the CIDR ranges for pods. And then the second and the third problem, so routing the traffic from service to the pods and keeping track of the pods. So this is solved by a Kubernetes component called kubeproxy, and kubeproxy uses either IP tables or IPVS, IP virtual server, to solve these two problems. So what the kubeproxy controller does, it connects to the Kubernetes API server, and it watches for any changes to the services, any changes to the pods. So whenever a service or a pod gets updated or changed, kubeproxy goes and updates the IP tables rules, so that the traffic sent to that service IP will get correctly routed to one of the backing pods. Actually, it's going to be correctly routed to one of the pods that are actually up and running, right? So then as the pods get destroyed or you create new ones, kubeproxy will update the rules in the IP tables to either add an IP address or remove an IP address or change an IP address, right? So when the packets are sent from a client pod to the service IP, they'll get filtered through those IP table rules. And as part of that filtering or going through the IP tables rules, this is where the destination IP, which is the service IP address, right, will get changed to one of the IP addresses of the backing pods. So let's say my service from the client pod, I'm sending a request to 1096.1.1, right? That's the service IP. What happens through the IP table rules is that that destination IP gets changed to 10.244.1.2 or one of the backing pod IPs. Then on the way back, so when the destination is sending back the request to the client pod, the destination pod IP address, so IP table rules again, will change that IP back to the service IP. So your client or the source pod will think that it's receiving the response from the service IP. So looking at the question, so what happens if no more IPs are available for new pods in the network? Yes, Marino's going to answer it. Thank you, Marino.
Yeah, so there's a couple of ways you can handle it, especially now with an updated version of Cilium, in which you can deploy multiple IP pools or pod CIDR IP pools, and they can be treated as IPAM pools, meaning if you ran out of or you exhausted your CIDR range, I don't know, let's say you had what's the max that you can do on a node anyways, 100 pods. Let's assume that you maxed that out first before you maxed out your CIDR range. You could still do one of two things. You could either increase the size of your subnet so it becomes maybe a /23 instead of a /24, so you have more usable addresses. Or the other option is you can have those multiple IP pools in which once an IP pool gets exhausted, then another one can be sourced and used just to be able to hand out to various pods that do come online. But the other consideration too is like, do you have pods that are still online that shouldn't be online? And that should be terminated and removed. And what are they doing? Are they just consuming IPs for no reason at all, right? Consuming unnecessary network space or real estate.
Yeah. Hope that answers the question. So pod to service, basically IP tables make sure to change the IP address as needed to either the destination pod, and then on the way back from the destination pod to the service, so that whoever the caller is sees the response as if it's coming from the service, not from that pod, backing pod directly. So the last question that like we need to answer when talking about like network in Kubernetes is, how do we deal with the communication or packets that are exiting the cluster? So if a pod is making a call to an API running outside the cluster, and also how do we deal with the packets that are entering the cluster. So someone from the internet calling to a service and then to the pod. So for egress, so on the way out, right? So the IP tables will make sure that the source IP of the pod will get changed to the internal IP of the node, so of the VM, right, where it's running. Now, typically, when you're running a cluster in the cloud, so like a managed or a cloud-hosted cluster, the nodes will have the private IPs, and they typically run inside a virtual private cloud network. And then, in order to allow the nodes to access the internet, you need to attach an internet gateway to the VPC network, and that gateway is going to perform the network address translation (NAT) and change the internal node IP to the public node IP. So this will then allow, so once that goes out, this then allows the response from the internet, right, to get routed back to the node and then eventually to the original caller. And then on the way back, the same translation is going to happen, but in the reverse order. So public node IP is going to get changed to the internal node IP and then back to the service. Now, if we talk about ingress, getting the outside traffic inside the cluster, we need a public IP address. So there's a Kubernetes service type called load balancer that allows us to get an external IP address. What happens here is behind the scenes, again, running in a cloud provider, right, let's say, or if you're running Kind using Metal LB, right? So there's a specific controller that's going to create an actual load balancer instance that's running in the cloud, and then that load balancer will have an external IP address you can then use to send traffic to or do things like hook up your custom domain and stuff like that. So when the traffic arrives at the load balancer, it's going to get routed to one of the nodes in the cluster, and then the IP tables rules on that chosen node will kick in and do the necessary NAT network address translation, and then direct the packets to one of the pods that's part of that service. Now, one thing here, you don't want to create a load balancer service instance for every service you want to expose, right? You ideally want to have typically a single external IP address, right? And then have the ability to serve multiple Kubernetes services behind that. And the way you do that is by using a ingress resource or an ingress controller. But that's beside this topic. I think Alessandro, the two of us talked about, right, API gateway, and you did a good explanation of like how we went from the ingress controller and ingress resource to actual API gateway and how that works. All right. Kube proxy. So what is Kube proxy? It's just a network proxy that runs on each node in the cluster, and it's connected to the API server and is responsible for keeping the services and the backing endpoints, the pod IPs, up to date. And it also configures and manages the routing rules on the nodes. There are 4 different modes that kubeproxy can run in: IP tables, IPVS, user space, and kernel space, and all these rely on IP tables. So user space is something that should not be used anymore. Basically, a kubeproxy in this mode runs as a web server and then routes all service IP addresses to that web server using IP tables. Kernel space is Windows only, so it's an alternative to user space, but for running Kubernetes on Windows nodes. And then IP tables, this relies on IP tables. This is the default mode. However, IP tables can become slow when there's a lot of rules. So let's say a 5,000 node cluster with 2,000 services and 10 pods will cause at least 20,000 IP tables rules on each worker, right? So that can be very slow to update and maintain. And also IP tables offer a more limited load balancing. So the next one, the IPVS, IP Virtual Server mode, is a more performant alternative because it does support multiple load balancing modes. So you can do round robin, least connection, destination source hashing, and so on. Compared to IP tables, which means that the load is also spread more evenly and effectively. So CNI, what is CNI? It's a software between the container runtime and the network implementation. The CNI project is a collection of specifications and libraries for developing plugins that configure the network interfaces in Linux containers. Practically speaking, the CNI plugins are called by the container runtime whenever a container gets created or destroyed, right? And then the CNI plugin is then responsible for connecting the container's network namespace to the host network namespace and assigning the IP addresses to the container, so doing the IP address management and setting up any necessary routes. So the container runtime takes in the configuration that specifies like a general or generic network information, things like subnets, and then it sends different CNI commands to the plugin, and then the plugin itself then goes and configures the network according to the configuration. Examples, Cilium, that's what we're going to talk about this week. Flannel is another example of a CNI. Calico, AWS VPC CNI, that's meant for clusters running on AWS, Azure CNI, and so on. Briefly about the spec, it's just a contract, right, between runtime interface and the plugin. It specifies only 4 commands that every CNI plugin has to implement. So the add command that gets called when a container gets created, and it needs to be added to or included into the network. The delete command that removes the container and releases any resources. Check, that just checks whether the network is set up properly. And then the version command is going to return the CNI version that's supported by the plugin. Plugin is implemented as a binary. So it's just a binary that runs on the host, and it takes in the configuration with the settings that define how to do like IP address management and how, if needed, to invoke any other plugins, because these plugins can be chained together. There's a question. I don't know if, Alessandro, you answered with your comments. So does the reverse DNAT rule, i.e. from 10 to source pod being source netted to the service IP, happen automatically as part of session tracking, as I couldn't find it in the IP tables rules? I'm not 100% sure, Marino. Do you know if? I think there might be a rule for that in the IP tables, but I'm not.
Yeah, so does the reverse DNAT rule from 10.244.1.1 source pod being source netted to the service IP happen automatically?
Part of session tracking might be. I'm not. I'm trying to look at my notes if I have anything.
Yeah, I'm gonna look into that. Yeah, it's just I have to think about that for a second as well.
All right. Well, we'll get back to you, Kareem, on that one. Is it possible to integrate Cilium on EKS with AWS VPC CNI? Alessandro, you've done some AWS.
Yeah, well, we've been looking into this. Actually, I have a link to a gist from one of our colleagues, Donjan, that explained this problem with Cilium and EKS, but it's possible. Yes, it's totally possible.
Yeah, you can. Yeah. There's also documentation page that talks specifically about that. How can you set up Cilium in combination with AWS's CNI plugin, right? All right. So IP address management. I briefly mentioned this earlier. So what IP address management defines, as the name suggests, is how the IP addresses get handed out to pods. So, for example, when like I mentioned, kind, right? When you install kind, the default CNI is kindnet, and then the kindnet is using a CNI plugin that's called host local, and that uses the IP range that will give out the IP addresses, and it's also going to maintain a local database of already allocated IPs. So when you're using Cilium, you can pick which IP address management you want to use. The default one that Cilium uses is called Cluster Scope, and it uses a Cilium node resource. And in that resource, within that Cilium node resource, you can then provide the CIDR range for each node where you want to where you want the node to give out the IP addresses from. The Kubernetes host scope is going to delegate the IPAM to each node in the cluster. It uses the CIDR ranges in the node resource. And then the CRD backed option, what it does, it allows us to delegate the IP address management to some external operator. So you would use this if you want to implement your own IP address management. And there's a collection of modes that are specific to cloud providers. So Azure, AWS, and GKE, which uses host scope pretty much. Kube proxy replacement. So this is another thing that's talked about because like I talked about what Kube proxy is and what it does. So Cilium has a setting that's called Kube proxy replacement, and it can be configured in several modes. So you can configure Cilium in such a way that it will completely replace the Kube proxy or whatever Kube proxy is responsible for, or if it can also coexist with the Kube proxy. That's in case if the Linux kernel your nodes are using do not support full replacement. So when you're running Kube proxy and Cilium eBPF replacement together, you have to understand that they are unaware of each other. And that's important, especially when you're installing Cilium on an existing cluster that already has existing workloads. So there's 3 different modes. So the first one is disabled. So all the functionality is going to be performed by Kube proxy. So that means Cilium CNI is not going to be involved in any Kube proxies work or responsibilities. The strict one is going to fully replace the Kube proxy functionality. And in that case, Cilium will take care of handling Kubernetes services like cluster IP, node IP, load balancer, external IP, host port services. Now, in the strict case, if you select this one, if you're running your nodes where the Linux kernel requirements are not met, the Cilium agent will fail. And then the partial one, this is a hybrid setup where a Cilium will partially replace Kube proxy's functionality. And by partially, what that means is that you will have to specify which functions you want Cilium to take over from Kube proxy. So it's like a middle ground in a way. All right, so eBPF and Cilium. So eBPF was another thing that was mentioned in the definition. So we mentioned that Cilium uses eBPF to provide secure and observe the network connectivity between workloads. So what eBPF allows us to do is allows us to run sandbox programs in a kernel without going back and forth between like kernel and user space like the IP tables do. So IP tables are running in the user space. So the image on the slide shows the difference between the user space and the kernel, I guess. So kernel is that layer that's between the hardware and your applications. So your applications are always running in the user space. And the kernel will handle things such as the networking, memory and process management, files, and so on. So your applications, they will typically run in the user space in an unprivileged mode, which means that they cannot directly interact with the hardware. What they do, or what they can do, is they can access any kernel functionality through system calls or syscalls. So one of the features of the kernel is that it allows us to write custom programs and then dynamically load them into the kernel and execute them. And this is the feature that's called BPF or eBPF. As part of this, the kernel supports hooks, and I'll talk about this in the next slide after the next one. But there's basically hooks that you can attach your programs to, and then the kernel will run those programs on like specific event, right? Oh, the packet is received. Well, we can run this program then, right? So which means instead of processing the packets through the chains and rules and the IP tables in the user space, we can write specific C programs, attach them to the hook that says on package received. That's not the real name, but just to explain, right? And then those will get automatically executed at those points. Brief history. I'm not going to go through this. So eBPF came from a feature called BPF, introduced in 1997. So the idea was that one could write some code or filters and then have those executed within the kernel. So an example here would be just like you have an Envoy proxy where you have filters, right? And you can write your own filters and then have the Envoy proxy run them as part of the flow. Similarly, eBPF allows you to write the programs that then get executed at certain points in the kernel, right? During the years, like there's been a lot of like evolution. BPF became eBPF in 2014. 2 years later, then the Cilium was announced. There's a great video by Alexei. I have it in the slide. We can probably post the link at some point, and he goes through the whole history of what started as BPF, what it was, and then how it became eBPF, and all of the things that happened throughout those years. So here's just a slide that demonstrates like packet flow, right? If you think about a process or application sending a request to outside of the node or somewhere to a different node, the packets go through the IP tables, rules, and chains to the virtual interface pair, and then through another IP tables configuration that's set on the node in order to reach the node's interface. So all the magic sauce, right, that tells, hey, if you're coming from here, you should go there. And then if there's a packet that's received here and it has a destination IP that falls under there, you should go there. So all that is defined in these IP tables rules. So what eBPF allows you to do is allows you to bypass those IP tables that are defined in the user space and do everything in the kernel instead, right? With those programs that are attached to the kernel. I think I mentioned this indirectly, but the usage of, well, the ability to use eBPF is dictated by the Linux kernel version. And if there are some capabilities that are not available in the kernel, Cilium is going to use IP tables implementation to satisfy that configuration or that routing. I get a drink. All right. So kernel supports set of BPF hooks in the networking stack, and then Cilium uses those hooks to attach the programs to it. So the first hook that you'll read about or can read about is Express Data Path BPF hook, or XDP. And this is the data path that's used for sending and receiving network packets at a high rate. And the way it does that is by bypassing most of the networking stack. So as soon as a packet is received, this hook will trigger, and then you can run a BPF program before any other processing happens. So XDP, this is typically used for DDoS mitigation, and then managing the packet flow, right? So it's the fast one, hence the name Express, right? Runs the first before any other processing happens. So the next hook is the traffic control ingress egress. It's similar to XDP. However, the programs that are attached to the TC hook run after the network stack does the initial processing of the packet. So these hooks will run before the L3 layer on the stack, but it will have access to most of the metadata that's associated with the packet. So typically these hooks are used for applying the L3, L4 endpoint policies and then redirecting traffic to endpoints. So I mentioned before that we have that virtual Ethernet pair that connects the container to the host. So if we attach a BPF program to each end of the pair, Cilium can then monitor and enforce policies on all the traffic that's entering or exiting the node. Also, another benefit of running these programs later in the stack is that we get more context, more metadata around the packets. The other two hooks used are the socket operations. So this hook gets attached to a specific C group and then runs on TCP events. Cilium attaches a BPF socket operations program to the root C group, and then it uses it to monitor the TCP state transitions. And then the last one is socket send receive, and this runs on every send operation performed by a TCP socket. And this is where the BPF program can look into the message, inspect the message, and either drop it, send it to the TCP layer, or just redirect it to another socket. So some of the features, like I already talked about, load balancing indirectly, right? So Cilium, when you deploy Cilium, it's going to ensure that you have the connectivity between the workloads, and it's also going to set up load balancing between services and pods. Another feature that we'll talk about more tomorrow when we talk about the network policies is Cilium's ability to enforce network policies. By default, Kubernetes ships with a custom resource called network policy. However, it doesn't provide an implementation for it. Cilium, as one of the CNIs, that is the one that provides an implementation for the network policy resource, which then allows us to apply policies. So network implements the network policy, but also defines its own Cilium network policy that has, it's more feature rich, I guess, but we'll show this tomorrow. Also, Cilium does use Envoy for any L7 policies or any L7 paths. Also, as the packets travel through the networking stack in the kernel, Cilium has the ability to provide us the visibility into the traffic flows. There's a UI component called Hubble. There's Hubble UI, there's Hubble CLI, and it allows us to inspect and view those flows. And then finally, you can also configure encryption using IPsec or WireGuard between the nodes and endpoints. Finally, an architectural diagram, I guess, or like a high-level view of the different components. Cilium agent runs as a daemon set, and there's one agent per node, and this is the component that talks to the API server, and it also interacts with the kernel, so it loads the eBPF programs, updates eBPF maps, and so on. It's also talking to the Cilium CNI, so it gets notified whenever new workloads get scheduled, and then it's also responsible for starting an Envoy proxy when needed. CNI plugin installs the CNI onto the hosts, and it will configure the node CNI to use the plugin, and then talks to the Cilium agent through the host file system socket. Hubble relay, which provides the cluster-wide observability and connects to the Hubble gRPC services that each Cilium agent exposes and provides. And then there's also the Cilium operator, which is used for cluster-wide one-time operations one would do. So briefly about, and we'll talk about this more tomorrow when we get into the network policies. So concept of endpoint in Cilium is a collection of containers or applications that share the same IP address. So basically a pod. By default, Cilium will assign an IPv4 and v6 addresses to all the endpoints, and then you can use either one to reach the endpoint. Each endpoint will also get an internal ID, like an endpoint ID, and that's going to be unique within the node. And the endpoint will also have a set of labels that can get derived either from the pod or from the container. So like Kubernetes labels, service account name, pod namespace, and so on. So these endpoints get created whenever you start a new pod, and that also kicks off the creation of Cilium identity. So Cilium identity is assigned to all endpoints, and this is what is used for enforcing the connectivity between the endpoints and the policies. So the identity is derived on the labels that get assigned to the pod. So if app HTTP bin or whatever version number, whatever you have in the labels. So if you change any of the labels, the identity of endpoints will get updated as well. Now pods can have, of course, multiple labels. And some of them are not really relevant or useful for identity. So things like timestamps and hashes. So Cilium will exclude automatically some of the labels that are not relevant for identity. But this is all customizable, and you can figure out and create and configure your own patterns. And there's also some well-known identities like kubedns, Cilium operator, and so on. All right, Alessandro, do you want to take it over? I'll stop sharing, and and while you're setting up, I'll take a look at the questions.
Yeah, there is a question that just came in from Uni about Cilium providing encryption using IPsec or WireGuard. So do we need a service mesh? And that's an interesting question because you have to think about the layer in which encryption is being provided at. So the layer at which encryption is being provided at is the wire level. So we're talking about node level encryption. We're not talking about pod level encryption. Yes, the pod's data path may be flowing through the node, but when we're talking about encryption, when we're talking about how pods and services communicate with each other, TLS not only offers encryption, it's also offering the identity piece, something that IPsec and WireGuard don't directly do.
Yeah. That's a good. Yeah, in service mesh, you actually by like doing the certs and mutual TLS, you're also like you're getting a identity per, let's say, per pod, per service account, if you wish, but also getting encryption that's specific. It's negotiated between the two different different endpoints, while in the Cilium's case, it's on the wire, and it's the same encryption regardless which endpoints are communicating. That's what I want to say, right?
Yeah, totally.
And I see Kareem's question. I'll answer to Kareem. I'll have to think about that one, but I'll answer it. We didn't miss it.
Cool. Yeah, that's so I try to catch up also with the questions, but indeed, I don't know if you remember this plugin WeaveNet, right? So from WeWorks, that was doing encryption between nodes back in the day, and didn't really took off. So it's not about encrypting traffic simply because it goes through the nodes, but it's also encrypting traffic using certificates, which doesn't happen in the case of WireGuard, as Marino explained. But all right, so I don't have a lot of time left. I mean, at least because I reserve an hour, but let's see where we go.
I mean, feel free to go over. I think if we have a demo, right? I think it's gonna be
short demo. So share screen.
Can you do it?
It's only one tab. Let me see if I can share the whole screen. Maybe it's better because switching between tabs is not great. So this is the screen. I think you see.
Yeah, let me add
See
it.
everything, right?
Yep.
But yeah, all right. So just about the installation, right? So very similar to Istio. Of course, Cilium wants to give you the Cilium community, and the project aims to have like a very simple onboarding, very simple experience to get Cilium installed. Being the CNI, most of the time, it's the first thing you install, so it gotta be very simple to get it done. So there are two ways, of course. There are two main ways. There is the Cilium CNI, so Cilium CLI. It's not Cilium CTL, but of course, it's the Cilium CLI. That it's simple to install. I installed it with Brew on my Mac, but you can download the release from the Cilium GitHub page and install it. Available for all major architectures, so it's something that it's, of course, is an imperative way. I'm not particularly inclined to use CLIs. I don't know you folks, but I stay away from CLIs because it's I like more Elm and more declarative ways to install things on my clusters. But it is there, and it's not only, it's like istio-ctl. It's also a command line that helps you troubleshooting, can verify if your cluster is ready to receive Cilium, is ready to be deployed. I can also verify the components they are correctly deployed. I can do a bunch of more tricks, including automatic proxying to the dashboard, which is Able, of course, and so on. So this is one way, and I'm not going to demonstrate that because it's so simple, right? So you just have to run the command Cilium install. Normally, Cilium install is enough to get up and running, but of course, you can use Cilium install with all the possible Elm values, right? So everything that you can set through the Elm values file, which is right here, of course. So this is the Cilium. I don't know if it's big enough, but it's part of the Cilium repository. Of course, there's a folder called install Kubernetes Cilium, and then this is the Elm chart. It's one single Elm chart for everything. I like this approach more than other projects where they split the Elm charts in multiple subcharts. Instead, for Cilium, there is one single Elm chart that does everything. Even Able is part of this. Other components are all deployed to the Elm chart, and so you can look at the values file. For example, you can see that Able is definitely enabled by default. You can tell. So, and all these parameters, you can override them at the command line of the Cilium install, or of course you can go full on with the Helm chart and install it via Helm. And it gives you exactly the same options, of course, because they expose the same API, the same way of deploying. It's just more maybe idempotent because you can do Helm upgrade and keep upgrading the Helm release for Cilium. You can do it with the command line with the Cilium CLI as well. But if you are deploying a bunch of stuff with Helm, you probably also want to do this via. You also want to do the CNI Cilium through to Helm. So a few things I'll show you very quickly. So as we said, we said so. Cilium is a CNI, right? So I deployed a Kubernetes cluster, and I use the bring your own CNI for AKS. So I'm in the team. I'm the one that loves Azure because I come from that school. So you can actually create clusters with the option, and this is the command line I used. It's somewhere here. So yes, so you can use this network plugin none, which doesn't deploy any CNI in AKS, right? So it's a after the deployment is done, it's a bare cluster. There is not even a CNI. In fact, I don't know if you can see it, but it's non-functional because it's missing a CNI. There are pending pods, so the pods are actually running in your cluster like core DNS. These pods are not functional because there is no CNI. So the first thing you do when you have a cluster like this is to install a CNI. So by design, this mode of deploying AKS requires a second step from the user, which is to deploy a CNI of your choice. In this case, we'll deploy Cilium, which is what we're talking about. It's definitely also one of the most popular, also in Azure. Azure also offers you the Azure version of Cilium, so you can actually install already a cluster in AKS with Cilium enabled, but you also have less choices of options. So you can, for example, replace kubeproxy in this way. So you need to stick to what Azure engineering decides that is the same defaults. You don't have the same degree of choice. So two things that really comes to mind when you install Cilium in this case. So we want to install Cilium with full replacement of kubeproxy, right? So we want to we don't want kubeproxy. We don't want anything to do with kubeproxy, even in Azure, in AKS. So, and one reason that we need to pass the API server and the API server port is that the Cilium agent on the node needs to know where to find the Kubernetes API server. So otherwise, we will not be able to download the configuration from the API server. So we do need to pass these two parameters at the command line of Helm, and so we just extract the endpoint for Kubernetes, the port, of course, and the URL. And using these two parameters, we just run our Helm command, which says install Cilium. I don't like to specify. I mean, you should specify the version of command line because I always like to run the latest. I think the latest is 1.14.5 or something like that. But you should also specify pin to a specific version. I don't do it, but it's something that you may want to do. And this is important. The kubeproxy replacement is true, so the kubeproxy will be completely replaced in functionality by eBPF and Cilium. And importantly, we pass the service host and the service port, the Kubernetes API. And this is a flag that enables a bunch of stuff in the Helm chart. If you look at it, in Helm, right? So you can go to Helm and of course search for specific. Normally, of course, it's not enabled, but when you do this, a bunch of things happens in the Helm chart that that will trigger the configuration of this specific to bring your own CNI, which is completely different from other scenarios where you don't where you don't have this. And of course, and node init enabled. Of course, this is also is the node initialization daemon set, because the nodes don't have a CNI yet, right? So there's nothing there. So you need to install a CNI. I think also creates the etc CNI.d and so on. It makes it makes this possible. And then when you do this, of course, you have this also install Abol, as we said, right? So, and then you can get the pods. You can see that the pods are being created, and there's Cilium. There's an init pod. These are actually running. There's 6 init containers in those Cilium agents on the node, because only one is the actual container that is running all the time. This is the app container of the pod, and all those 6 out of 7 are actually init containers that prepare the node. And you can see that as soon as I have a CNI running, my metrics error, my core DNS, they become available, right? So they pick up they get an IP address assigned, because now a CNI is available to assign those IPs, and they're actually up and running. And now, after a few seconds, I have a working cluster. So, and this is the Cilium node. The Cilium node init runs on every node, initializing the CNI. And I think Abol is not there, but we maybe enable it. You can also do Cilium. And so Cilium, as I say, is a command line that can also verify the configuration. So you can, for example, do what was it? Status shows that Cilium is perfectly deployed. There's a bunch of stuff, and you can also do Cilium Abol install. Enable. This will also enable Abol. So deploy the deployment for Abol. You can check the status, Abol relay OK, and then you can do Abol port forward or Y, also possible. This should open. It's probably still coming up. Thought this was enough to enable Abol, but I don't. Abol relay. Well, let's keep Abol for now, but we will come back. Do you have any idea why it is not working, guys?
I'm not. I can check my notes if there's anything. Let's see.
Can you share your thing again?
Yep.
Yes. So you did Hubble enable, right? And then port forward is failing, right?
Yeah.
Is there anything like deployed? Is there a service that's running?
Yeah, there's a. Let's see. There's a Abol relay. There's no Abol Y service. I thought it was deployed with the Abol enable, but where to. This should also be part of the certification, right? So I think it's part of the certification. I didn't try myself. I thought it was it works on kind actually, but
yeah. Never mind. I will.
wait.
I will show. Well, Is it work? Is it up?
Yeah, it's enable minus y.
Oh, you have to specify the.
Yes.
Yeah.
And now, very soon, you have an able y service, of course. And now you can do able y. They should automatically port forward and open the able y in your browser. So that's how you get to the UI. Of course, there is not much in this cluster yet, but you can already see some things, of course. Yeah, so that's how you get up and running with Cilium on AKS, but also works on client. Pretty easy. I have a few more notes, of course. Like there are two ways. I was reading about this. Of course, there are two ways to deploy. There are literally two. There's a switch in the Helm chart about the routing mode. So the tunnel is the default way, and encapsulate traffic going from node to node in VXLAN. So this is what is happening now, right? So we have the routing mode set to tunnel. You can tell when you do Helm ls -a Helm get values -s kubesystem Cilium minus so you can tell the routing mode. Yeah, it's empty, which means it's tunnel, so that's the default. While there is a new way, there is a new mode, of course, the native way, the native routing, which delegates to the underlying network the routing of traffic. So it assumes there is a local routing available for the packet. So Cilium doesn't make an assumption how to route those packets to another node. So assumes there is an underlying routing table, there's an underlying mechanism that will route the packets to the other node. So the Linux networking knows what to do with the packets. So that's one thing I wanted to talk about. Last thing, it's about some gotchas, of course. So ambient and Cilium. So because we love Istio as well. So just a few things about Istio and Cilium. Yet Cilium and ambient don't work just yet. The support is being worked on. There's of course like a lot of work to be done when you think about it. Ambient does redirection, so redirects traffic from the pods or part of the mesh into the Z tunnel, and eBPF and Cilium does the same thing. So there's a bit of overlap there, and people are working on it. It's we all hope it's gonna be released soon. And I was also checking this when you work with Istio Sidecar, the usual, the classic mode of Istio with Cilium, and you are on AWS CNI. There's actually a GIS from our colleagues, and also refers to the original Cilium issues. So in the case of when you want to run Istio D on AWS and you want to use Cilium, then you are forced to use host network, which binds the Istio D pod to the node itself, which is not the greatest way to run anything on Kubernetes, of course. But if you look through the issue, you understand why there's some issue specific to AKS. Again, not my thing, Amazon, but I understand it's also being worked on. It's also very active issue. So if you want to run Istio and Cilium on AWS EKS, you have to be careful what you're gonna get.
All right.
Any questions?
Yeah. I just noticed that I did the respond to Kareem, but he's commenting from LinkedIn, and the comments that are posted here are not going to LinkedIn. Sorry, Kareem. So
Go to
yeah,
YouTube.
so XDP applies on the Viet on the node, and then you were asking about. I'm assuming you asked, can you do it for a service? I do it for a pod usually. I'm assuming you were asking for port forwarding. And yeah, you can do port forwards to a service. I know it wasn't supported for a while, but then I don't know when it got added, but it's there now. All right. Well, thanks everyone. If we'll be back tomorrow. So if you have any questions that you didn't get to ask today, feel free to ask them tomorrow. You'll have another chance.
There's also we have a Cilium Slack, of course. I mean, we want to make sure that people know where to find us. We have our own solo Slack, but if you have questions more pertinent to Istio and Cilium, I think the best place is the Istio Slack. And if you want to join, of course, the Cilium Slack is also a great place to find more information.
Yeah. All right, everyone. Well, thanks for joining, and we'll see you all tomorrow again. Bye, everyone.